all, Miss Pasega here. So, have you ever wondered what your guitar strings do when you actually play an instrument? Well, good news and bad news. If you enjoyed that 7-second clip from the Weezer song, it turns out, yes, this person is great at playing the guitar. But unfortunately, that's not really what the guitar strings do. This effect where it looks like waves are going back and forth is most likely because of an artifact of the camera. So if we watch it again, because this camera is going too slowly to catch the wave, it looks like there's waves going back and forth and right and left, when really it's only making one harmonic. That harmonic makes noise that we hear, and it looks something like this. When you pluck a guitar string, the string only moves in the first harmonic, but you can hear all of the other harmonics because of something called resonance. So remember on Friday we worked with the 3 equations to deal with resonance. We were looking at the frequency, wavelength, speed relationships. But let's be honest, it's been a while. So just to review, when we look at the different natural frequencies of a guitar string, any 2 complete antinodes equals 1 wave. So in this case, 2 complete antinodes are 2/3 of the length of this string. Hence, 1 wavelength can be calculated by the equation 2 times L over N, where N in each case is the number of harmonics. This is the second harmonic because it has 2 complete antinodes. The second pattern I had you deal with was the relationship between the fundamental frequency, that is the first frequency, the main frequency that you hear, and its subsequent harmonics, the second, third, fourth, and in theory there are an infinite number of harmonics just with decreasing amplitude here. So if my first guitar string starts at 252.54 Hertz, that same string simultaneously, so we hear all of these notes at the same time, simultaneously makes another frequency at about 504 and 756 and 1008 Hertz respectively. So each higher harmonic is a multiple of my fundamental or first harmonic. My first harmonic is the most important, hence fundamental. It is also the one that I hear the highest amplitude with. Where it says magnitude, you guys don't need to know specific numbers on this amplitude or magnitude side, but know that your first harmonic is generally the loudest, and all the other multiples tend to be quieter. The final equation I had you look at was the relationship between wave speed, frequency, and wavelength. And please recall that the wave speed does not depend on frequency and wavelength. Frequency and wavelength are inverses of each other. Having a high frequency means you have a short wavelength, and having a long wavelength generally means that's a larger instrument, so it produces a lower frequency. Frequency and wavelength don't affect wave speed. Remember, wave speed depends on the medium it travels through. It might depend on the tension of the guitar string, the temperature of the air. It might depend on the state of matter that the earthquake wave goes through, or whether or not there's a material there at all, like in the case of light. But in either case, this is our third relationship. Frequency and wavelength are inverses of each other, and wave speed depends on the medium it travels through. So let's put this all together now. On Friday, you should have finished problems 1, 2, and 3 in this packet that we physically did together while doing notes on Friday. So what I want us to do today then is let's take it to the back page. And even though we won't be able to do this lab together in class as a team, we will be able to do this lab electronically. So let's read through the lab first, then I'll show you the procedure we're using. That way we can calculate together this wave speed. So this time we're looking at open tube instruments instead of string instruments. Remember from Friday that open tube instruments versus string instruments will have the same pattern of antinode, node, antinode, node, antinode repeating themselves, except that our open tube harmonics have antinodes on both ends as opposed to nodes. I know this is my second harmonic because it has two complete antinodes. A half plus 1 plus a half equals 2. Okay, so I want you to draw the first 4 standing waves. Then label the wavelength on each diagram. Please note that your first harmonic's wavelength will probably go out of this box. If my first harmonic has 1 complete up and 1 complete down, that wave is probably bigger than the box I provided because the wavelength itself will be longer than the tube or string or whatever instrument we're talking about. Okay, so one difference between the lab you are doing and the lab that everyone else did during class is in this case, I'm not having you measure the length of one boomwhacker. I'm going to have you take the wavelength at different harmonics. In the simulation, I'm going to have you measure the length of the boomwhacker. It should be listed on the bottom of the simulation, and use that to calculate the wavelengths for the first 4 harmonics. 2, 3, 4. Okay. Now, it says to measure the harmonic frequencies using either method demonstrated in class. Well, you're only going to be able to do one, so let's show you how that works. Once you get to the Resonance Tube Lab at physicsaviary.com, we want to find the resonant frequencies of this tube. So what I want you to do is click the tube to change its length to the longest it can possibly be. Then we're going to try and figure out the speed of sound using just this tube. We're going to measure its length and therefore be able to calculate its wavelengths. I'm going to show you with the cap on. Please remember to remove the cap like this when you do your experiment. With the cap off, this represents something like a flute or a pan flute, maybe a harmonica. With the cap on, this is going to give me harmonics closer to like a clarinet or other woodwind instruments. So I'm going to hit scan, and what this is representing, and I super wish that this had sound to go with it, is it's having this increase in frequency until a standing wave is created. So it creates a standing wave, it's automatically paused for me. In this case, there's a node on one side and an antinode on the other, but that's because the cap is still on. You're going to remove it later. So I'd record my first frequency and then continue scanning until the second frequency comes up. Shortly. Anytime now. The second frequency. Go. Oh gosh, it's going to be a while. If you notice that it goes all the way up to 250 without making any additional harmonics, you can also change the range selection here. Oh, it might. All right, didn't make it. Change the range selection until it finds the next one. Okay, so let's reiterate. First, draw the standing wave diagram for the first 4 harmonics. Then, label the wavelength on each diagram. Measure the length of the boomwhacker. I want you to pick the longest length and take the cap off of it. And use that length as capital L to calculate the wavelength for the first 4 harmonics. Then, scan through the frequencies and record the first 4 frequencies that give resonance in the tube. And finally, use that together, wavelength times frequency equals speed, to figure out the speed that they're using in the simulation. So, in our case, you probably shouldn't have any human error, but we will see. Best of luck. Oh, P.S. And when you're done, remember to upload this to Classroom so that you can get credit. For this assignment, I'm only looking for the back page of the lab. you should have already turned in the other page 1, 2, and 3 on Friday. Right? Thanks. Have a great night.